now that we've gone through several rules for assigning oxidation numbers, you may ask yourself, why do we need to even use these? So there are a few reasons of why we assign oxidation numbers. Number one is to keep track of electrons during redox reactions. Another reason came up earlier when we discussed nomenclature, and this is for naming compounds containing transition metals. So when we look at these transition metal complexes, remember we put the charge in the parentheses. So if we have titanium 4 oxide, this Roman numeral refers to the oxidation state of the transition metal sensor. So in these compounds, the oxidation state of the transition metal is going to dictate a lot of the physical properties of the material that contains that transition metal. So those are the two main reasons we look at this, and now let's go over some examples of assigning oxidation numbers for particular complexes. So the first example we want to do is to determine the oxidation state of chromium in K2Cr2O7. So when we look at this complex following our rules that we just developed, if we have K2Cr2O7, the sum of these oxidation states have to be 0. There are 2 potassiums, it's in group 1, so it's going to have a +1 charge. There are 2 chromiums, and the oxidation number of chromium is what we're trying to determine. There are 7 oxygens, and remember that oxygen in compounds like this has an oxidation state of -2. So the sum of all these oxidation states have to be 0. So we can use some algebra to know that 2 times the oxidation state of chromium is going to equal +14 minus 2. So 2 times the oxidation state of chromium is going to equal 12. So our oxidation number for chromium in this particular case is going to equal +6. So that's an example of how you would go through this. We now need to keep track of some of these examples during redox reactions, and we can actually identify which species is being oxidized and which one's being reduced. So for example, we can analyze the following reaction. 2 Mg solid plus O2 gas, giving us 2 MgO as a solid. In this particular reaction, the oxidation states of the various species change. On the left-hand side, we have both reactants in their elemental form. So in that case, magnesium and oxygen are both going to have an oxidation state of 0. But when we form compounds, the oxidation states of each of these change. Remember that oxygen is going to have a -2 oxidation state, which means that the magnesium has to have a +2 oxidation state. So we can break this down into each of the species that are going to be oxidized and they're going to be reduced. When a species is oxidized, it goes from a low oxidation state to a higher oxidation state. So in this particular case, the magnesium goes from an oxidation state of 0 to an oxidation state of 2+. So it's being oxidized. Whereas the oxygen, when we start with O2, it starts with an oxidation state of 0 and goes to an oxidation state of 2-. So it is being reduced. So in these particular reactions, we can identify the species that's being oxidized and the species that's going to be reduced. So let's look at one more example of this particular case where we look at a particular reaction and we can try to identify if a transition metal is oxidized or reduced. So the reaction that we're going to investigate is NH4 twice Cr2O7. The reaction that forms, it's going to decompose into Cr2O3 plus N2 plus 4 waters. So in this particular case, we can try to determine the oxidation state of our transition metal and whether that would be oxidized or reduced. So if we look at this particular complex, NH4 has a charge of +1, so that's going to be its oxidation state. There's 2 of them, so we multiply that by 2. Then we have 2 chromiums, and we also have 7 oxygens, which has an oxidation state of -2. Now when we go and try to investigate what that oxidation state is, this complex is not charged, so it's going to have the sum of their oxidation states to be 0. So if we do the algebra, we can see that the oxidation number of chromium is going to be equal to +6. So on the reactant side, chromium has an oxidation number of +6. On the product side, we have Cr2O3. So we have 2 times the oxidation state of chromium plus 3 times the oxidation state of oxygen, which is going to be -2, has to equal 0. So here we have 2 times the oxidation of chromium is going to equal +6. So our oxidation number for chromium in this case is going to equal +3. So if we go from +6 to +3, we're going to call this reduction, because the oxidation state goes from a larger number down to a smaller number. So we can try to investigate what happens to each of these complexes. Now, when something is reduced, it has to be accompanied by an oxidation. So the question is, which species in here becomes oxidized? So we now have to look at the reactant and the product side to see what's oxidized and what's reduced. If we look at this particular complex, we can look at NH4+, okay, because that is our cation in this particular compound. Okay, we know that in compounds like this, hydrogen has an oxidation state of +1. There's 4 of them, plus the oxidation state of nitrogen has to give an overall oxidation number of +1, because that's the charge of this ion. So in this case, our nitrogen is going to have an oxidation number equal to -3. Over on the product side, we have nitrogen existing as N2, which is in its elemental form, so the oxidation number of nitrogen here is going to be 0. When we go from +3 to 0, our number is getting larger, so we call this oxidation. So in this reaction, chromium is reduced and nitrogen is oxidized. And one of them would not happen without the other. So this is how you would investigate various reactions and assign oxidation states to each of the species in a particular chemical